Illustration number 5. Prove that the ratio of rate of change of gravitational acceleration at height equal to the Earth's radius from the surface of the Earth to the value of g at the surface of Earth is equal to minus 1 over 4 re. So, the gravitational acceleration at distance r greater than or equal to re from the center of the Earth is g of r is equal to gm over r square. So this is my first equation, and now I am differentiating this particular equation with respect to the distance, means r. So differentiating equation 1 with respect to r. Therefore, d of gr divided by dr is equal to minus twice g m, and for simplification that this is the mass of Earth, I am writing me divided by r cube. And here the value of r for the substance or the body outside of the Earth, the distance is given by re plus h, but here the height is same as the radius of the Earth, so it is equal to re plus re, that is equal to twice of re. Therefore, small r is equal to 2re. And now, substituting this value in equation number 2, therefore dgr over dr at 2re is equal to minus twice gme divided by 2re cube, that is equal to minus 2 gme divided by 8re cube. So, the surface of the Earth acceleration is given by, means g at e is gme over r square. So, let me divide this equation number 3 by equation number 4. And therefore, dgr by dr at twice of re divided by g is equal to minus twice gme over r cube, sorry, it is 8r cube, or in particular re cube, is divided by gme over re square. So g and me are cancelled out. re square is cancelled out by re cube by putting one re as it is, and therefore this ratio, if you simplify, minus 1 over 4 re and therefore the ratio for the rate of change of acceleration at the height equal to the Earth's radius of the Earth's surface and the value of gravitation acceleration at the Earth's surface is equal to -1 upon 4RE, and hence the result is proved. Let's start illustration number 6. We have to find out the period of rotation of the Earth about its own axis in terms of RE and G, that means in terms of radius of the Earth and gravitational acceleration, for which the effective acceleration due to gravity becomes 0 at the equator. So first of all, we have to consider at equator what are the properties. So the first property what I am consider over here is the latitude. That is lambda, because it is basically an angle, that is 0 degree. And at a place having latitude lambda on the Earth, the gravitational acceleration or the effective gravitational acceleration is G dash. We denoted it as G dash, and the equation for G dash is equal to G minus RE omega square cos square lambda, and this equation we have obtained earlier, so it does not need any much explanation. And here RE is used for radius of the Earth and G is the gravitational acceleration at the Earth's surface, and here you remember this is the value of gravitational acceleration without considering the rotation. Why? Because at the equator the value of lambda is 0. And now we have the time period or the angular speed of Earth's rotation that is related basically with the time period is equal to 2 pi over t. But we want to find out the time period t for which condition? For G dash is equal to 0 at equator. So for this condition, we will now obtain the value of time period t, and therefore substitute 0 in this equation. So 0 is equal to G minus RE omega square means 4 pi square over t square and cos square lambda, that is 1, because cos 0 is 1 and 1 square is 1. Now here you can see I can take this negative sign towards the right hand side, so I will get G is equal to RE into 4 pi square over t square. And now I make this time period t as an object, so what I will get? Therefore t square is equal to 4 pi square RE divided by G. And now taking square root on both the sides, therefore time period t is equal to twice pi under root of RE by G, and that is the equation for the time period at an equator at which the gravitational acceleration becomes 0. So this was illustration number 6, and now we will switch on to gravitational intensity, the another approach of this chapter. Illustration number 7, the gravitational intensity at a point is given by I vector is equal to 10 to power minus 9 I plus j Newton upon kilogram. And here the mass of the body is given, so we have to find out the magnitude of force. But before that, I am finding the vector quantity of force. So the force is given by F is equal to I into M, and here the value of I is given 10 to power minus 9 I cap plus j cap. So here you can see the field is in xy dimension and mass of the body is 10 kilogram. So 10 raised to minus 9 into 10, that is 10 to power minus 8 I cap plus j cap. And so the final value of force I can write down 10 to power minus 8 I cap plus 10 to power minus 8 j cap Newton per kilogram. And so, not Newton per kilogram, because it is the value of force only, I can write down only Newton. And so, modulus of F is given by under root of 10 to power minus 8 whole square plus 10 to power minus 8 whole square is equal to under root of 2 times 10 to power minus 8 whole square, that is equal to 10 to power minus 8 is outside and under root 2 is as it is. So this is basically the value of force, and if you want to extend, then root 2 is having the value 1.414 into 10 to power minus 8 Newton. F is equal to. Now, I have to find out the value of gravitational acceleration. Then according to Newton's second law of motion, it is F over m, that is equal to 1.414 into 10 to power minus 8 divided by 10, that is equal to 1.414 into 10 to power minus 9, and don't forget to write down the unit meter per second square, or you can write down in this way ms raised to minus 2. So this is illustration number 7, in which we have find out the value of force as well as the value of gravitational acceleration. Now let's move on to the next approach of this unit, that is gravitational potential energy.